Here are solutions to homework set number 11 for ECE 111, Intro to ECE. In this homework set, we look at using Matlab to solve problems using RLC circuits with inductors, specifically using numerical methods to solve second-order coupled differential equations. Now that sounds intimidating, but with Matlab it's actually not too bad. So last week we looked at using capacitors. This week, we're looking at using inductors. Now, a capacitor is an integrator, and inductor is a differentiator. The relationship between voltage and current for an inductor is V is L di dt, so the change in current is proportional to voltage. So problem one is, suppose I have the current through an inductor as follows. What's the voltage? Well, if the inductor is 1 Henry, then the voltage is just the derivative of current. So to do that, the derivative is slope. So here the slope is 0, the voltage is 0. Here the slope is change in y over change of x is 1 over 2, 1/2. It's a jump up to 1/2. Now the slope is 3 over 1, jumps up to 3 volts. Slope is 0, jumps back down to 0 volts. And it can go negative. Here the slope is minus 5 over 1, drops down to minus 5. Now the slope is minus 2 over 2, minus 1, plus 3, then 0. So this is the voltage that I see across an inductor with that current. Problem 2 looks at analyze this circuit. This is an RLC circuit, and that looks really intimidating. It's actually not too bad. There's kind of a trick to it. What I want to do is say the current through the capacitor is IA plus IB plus IC. That's conservation of current. From before, the current through a capacitor is I equals C dV dt. And here I'm using prime to indicate derivatives. It's a little bit more convenient. So the derivative of V1 times C are all these currents. For an inductor, I know the voltage across this inductor is L di dt. Voltage across this inductor is L di dt. So I know that IC, this guy right here, the third current, is 0 minus V1 over R. So now I start substituting. C dV dt, that this guy right here, is all these added up together. That's your IA plus IB plus IC, and there's IC. Now here's where the trick comes in. I'm going to differentiate this equation. So C times the second derivative of V1 is the derivative of IA plus derivative of IB plus 1 over R minus 1 over R derivative of V1. Now that I have the derivative of IA and IB, I can substitute. Plugging those in, I wind up with a second order differential equation, or rewriting it slightly, a second order differential equation. Now if I plug in values, I wind up with this guy right here. So that's the differential equation at node 1. If you go back to the circuit, due to symmetry, all these nodes are the same except for node 4. What's different about node 4 is that there's no second inductor attached to it. They just have the 1. So the IB disappears for the last node. This term disappears on the last node. And so you wind up with just 1, and this term goes away. That's at the last node. All the equations are the same except for the last node. The last node's the oddball. This is a slightly different equation. So what I'm left with is with an RC circuit, last week's lecture, my circuit was described by coupled first-order differential equations. With an RLC circuit, adding inductors, my circuit is described by second-order coupled differential equations. Problem 3 says, okay, solve. Now, when you get to Math 265, you might solve problems like this. This is actually fairly hard to solve by hand. It's actually fairly easy to solve numerically. In Matlab, if I know the differential equations, integrate once, I get the first derivative. Integrate twice, I get the voltage. Plot the voltage versus time. I've solved my coupled differential equations. So let's do that. I'll say my voltage on the left is 10. My initial voltage is 0. The initial derivative is 0. Here's my integration step size, 0.01. I'm going to run for 3 seconds. So at any time point, I know the second derivative. I know the voltages. Calculate the second derivative. Now integrate once. This is Euler integration. Add to the old velocity, the current velocity plus acceleration times step size. I've got the velocities, the derivatives. Now integrate the derivative, I get voltage. Now plot the voltage. And here's what it looks like. If you recall last week when we did heat equation, a couple of first order differential equations, those are kind of sluggish. The voltage goes up and stops. And just for fun, let's run this for a longer time. Run it for 10 seconds. Well, instead of being coupled first order differential equations, these are coupled second order differential equations. Coupled second order differential equations behave very differently. This is called the wave equation. With second order systems, you bounce around. Unlike the heat equation, where you just warm up to a temperature and stop, this guy just keeps on bouncing. If you plot the voltage versus time, it's pretty erratic. But that's how it behaves. To see why it's called the wave equation, let's expand this out to 30 nodes. Well, with 30 nodes, I could make 30 copies of this. That's one way to do it. That's perfectly valid, nothing wrong with that, not stylish. Another way of doing it is using arrays. Let's define a vector, a 30 by 1 vector. That's all 30 nodes. And actually, let's just make this n. This just makes it more generic. I can have as many nodes as I want. If I just want 4 nodes, I make that 4. 30 nodes do 30. Now, on the left-hand side, rather than having the left point just be 10, I'm going to have this being a sine wave, kind of a snap. You'll see that in just a sec. I will then solve my coupled differential equations. But here, since I'm using vectors, I can just do ddv of n, go through a for loop, solve the differential equation for each node. The two oddballs are the endpoints. At the left endpoint, Matlab really hates the indices 0, so I'm going to use v0 rather than v of 0. v of 0 will crash Matlab. And the other oddball is the last endpoint. Again, this is a little bit different because there is no node 31, so the 60 becomes a 30. And we kind of saw that back over here. That last node was the oddball. All these are the same, except for the last node. So doing that, bring this up, I can sit there and simulate how this behaves with 30 nodes. Now this is why it's called the wave equation. On the left-hand side, that's what this is. This is just kind of a snap. It's like a string. You have this big long string, snap it, I launch a wave down the string. Strings satisfy the wave equation. RLC circuit satisfies the wave equation. And if you look at it, you see it looks like I'm launching a wave. The wave went to the right, hit the right endpoint, then reflected. Came back. It now hits the left node, reflects. Now I've got a negative reflection. So that's how the system behaves. Coupled second-order differential equations are called the wave equation. That's because it looks like you're launching a wave. Very different than a heat equation. Okay, so that's problem number 4. Problem number 5 says, well, let's take the two endpoints. The right endpoint, going back to the circuit. If I just leave this free like this, it's a free endpoint. What that one does is this. Let's just run it for 8 seconds. I'm going to launch a wave the wave travels down the waveguide, travels down the RLC circuit. That's my voltage propagating down. When I hit the right endpoint, watch what happens. This is a free endpoint. It snaps up to double the amplitude, comes back down to 0. Then I get a reflection. The reflection is the same amplitude or same sign as it came in. It's a plus reflection. So if the right endpoint, which is, let's get this out of the way, from right here, this is the resistor attached to that last node, and this guy right here. If I have that resistance being really, really large, meaning 1 over R is really, really small, I get a plus reflection. Now suppose I make that that last resistor really, really big. So 1 over R becomes 100, 1 over RC. Now what happens when I launch a wave, if you look at the right endpoint, the R is really, really small, so the voltage doesn't change much. This becomes kind of stiff, barely moves. It barely moves, but when it barely moves, I get a negative reflection. Okay, so here's a question for you. If this number is too small, I get a plus reflection. If it's too big, I get a negative reflection. Can I get no reflection? And the answer actually is yes. This is what you do in 351. This is called impedance matching. This is kind of an important concept. Wires behave like RLC circuits. They behave as transmission lines. At really high frequencies, when I send a voltage along a wire, it doesn't change all at once. It actually propagates, satisfying the heat equation. That's at really high frequencies. This is an issue because for computers keep on running faster and faster every year. At higher and higher frequencies, the wires in computers start looking like waveguides. If I do it wrong, I get a reflection, and this can cause a pulse trigger. To get rid of the pulse trigger, I want to get rid of reflections, meaning I want to stick a resistance at the end that's just right. That's my characteristic impedance. In EMAG, ECE 351, you'll calculate what that is. In this class, I can find that number just by trial and error. So 100 was too big, 0.01 is too small. Let's try 10. So I launch a wave, it comes down, hits the right endpoint. Right endpoint moves, and I've got a slight negative reflection. Okay, so that means that this number was too big. Let's make it smaller. Let's try 2. I launch a wave, it goes down the waveguide, hits the right endpoint, time passes. And I now have a plus reflection. Okay, so 2 was too small, 10 was too big. Let's try 6. This number right here, the 10, that's kind of arbitrary. I just wanted to be big enough that I hit the right endpoint, short enough that I don't hit the left endpoint. So here's the waveguide. The wave is going down, hitting the right endpoint. When 1 over RC is 6, that's pretty good. So that's probably what I want to do. That's the impedance that I want to stop all reflections. So that is homework set number 10. Just for fun, let's see what happens if the input is just a sine wave. And I change this last one to 0.01. Impedance matching is important in things other than just circuits, like bridges and buildings. If I have the ground shaking, cars driving on a truck, people walking, inducing sine waves, if I have improper impedance matching, what I get is this. The wave travels down, I get a reflection, then I have one wave going left, a reflection coming back right. Those waves start adding, and I start getting standing waves. So here you can kind of see the standing waves forming. If this number is too big, I get the same problem. Now the right endpoint barely moves. That causes negative reflections. The negative reflection and the plus waveform coming in start creating standing waves. Again, that can cause trouble. If we go back to that Goldilocks number, 6 seems about the right number to get rid of reflections. If there's no reflections, then there's no standing waves. So this would be much better. This would be a bridge, walkway, stuff like that. That's not getting these huge standing waves on it that cause the metal fatigue. I just have the small amplitude input going down, hits the right side. The energy is absorbed in that resistor. So that is homework set number 11 for ECE 111.